Okay, let's continue with the next talk that is given by Michael Schwarz from, I tried to say it in German.
Yeah, go for it.
Technische Universität München.
Yeah, that's it.
Is it right? Okay.
Yes. Tom, yeah, that's the easier one, yeah.
Tum was easy. Okay, and his talk is titled When Long Jumps Fall Short, Control Flow Tracking and Misuse Detection for Non-Local Jumps in C.
I just need to get it to mirror. Okay, so thank you for the kind introduction. I will be presenting our work that deals with this feature of set jump, long jump in C. This is joint work together with my colleague Julian Erhard and my colleague Vesal, Vojdani and Simmo Saan from the University of Tartu and my PhD advisor Helmut Seidl. So first of all, I don't know how up to date you are or how fresh your C knowledge is, so let's do a quick refresher such that everybody's on the same page. Namely, what does this feature set jump, long jump in C do? We have a very simple program here that has three functions, main, bar, and foo. And main, first of all, calls bar. And then in bar, you have this function set jump, and you provide it with a variable of type jump buff t. And what happens here is that the set jump stores the current execution state into the special variable of this type jump buff t. And then it returns 0. So there's nothing interesting going on here yet. Then the program continues. And then at some point you call foo. And inside of this foo, you then get some status variable from somewhere, compare it whether it is less than 0. And if yes, then you say, oh, I have encountered some sort of error. And what I do then is, in order to handle this error, I call this function long jump and provide it, first of all, with the jump buffer and then with this variable error. And what this does is it transfers control flow to the point where the set jump was last called. And then it appears as if the set jump returns several times. So it looks like it returns a second time, and this time it returns 42. So in some sense, one can see this feature as some sort of non-local go-to. And yeah, so in this program, then we just print some message and exit. However, if I slightly modify the program, then I immediately get a program that is buggy for a non-trivial reason. Namely, if I then here try to write this message into the log, I actually have undefined behavior in my C program here, because this variable log path has been modified between the call to set jump and the invocation of the long jump that jumped back, and therefore this variable has indeterminate value. So if I try to access it, then my program will blow up. So this is one of these pitfalls that we have here. And then another pitfall that's perhaps a little less surprising is if I try to invoke long jump and try to jump to a place where the corresponding function that contained the set jump has already returned, then there's nothing to jump back to. So this will also yield undefined behavior. And then the question people always ask is, why would you bother with analyzing the set jump, long jump? Most analyzers don't do it, they all ignore it. Why is it interesting? And to this we say, well, it's actually something that C developers use quite a bit for simulating exceptions in C. And there is some empirical studies that developers think it is important that static analysis tools also consider these exceptional flows and not just the cases where things go completely right. And then, as you have seen, the set jump, long jump, it has an intricate semantics, and developers, they maybe use it, but they don't use it day to day. So they might not be familiar with all of these pitfalls and all of these traps. So actually, it is a very good place for hard-to-find bugs to hide. So we would argue that one should not just aim to be sound in the presence of these set jump, long jump features, but actually we should develop analyses that also are able to flag all of these misuses. Now, what are these possible misuses? I basically have the two ones that we already talked about here in bold, but there is a whole suite of other issues. So this once again highlights that this semantics of the set jump, long jump is really complicated. And on top of cases where you actually run into undefined behavior, you have some other pitfalls that are perhaps even a bit funny. So for example, if you pass 0 as the second argument to this long jump, this is silently changed to 1, which is also something that a developer might not be aware, and maybe one should tell it to them if they are providing this argument 0 here. Okay, so then our analysis, it's happened in a setting where we are doing context-sensitive abstract interpretation, and we're doing this user-even partial tabulation. So if you think back to Sharia and Pinelli, this is their functional approach. And we are formulating this entire thing using side-effecting constraint systems. Now, what are side-effecting constraint systems? Well, they are constraint systems plus side effects. No surprise there. And the idea with the side effects is that you can have contributions not just to the unknowns on the left-hand side, but also to other unknowns in the constraint system. And this we have used in the past, for example, to accumulate flow-insensitive information during a flow-sensitive analysis, for example, for these thread modular analyses. And the reason why we think it's a good fit here is that we use it to avoid polluting the CFG with many extra edges. Because if you want to consider all of these cases where you could do a long jump to somewhere, then you would have to introduce a very high amount of edges into the CFG, because basically every function that you call could be left by means of a long jump that is somewhere down the call stack. And so this is very nice formalism here to avoid doing this pollution. Then we do a little bit of pre-processing. This is very mild. So basically what we do is we replace this one edge that we have for the set jump. We replace it with 2 edges. And we do this to separate out the case where basically the set jump returns for the first time. So this is the moment when you set the jump buffer. And then the second moment where the set jump actually returns for the second time, or further times. And here we also introduce these barred nodes. So here we have this node u bar. And these are basically the nodes that will account for the values that might reach there via long jump. And these barred nodes, they will receive their values via side effects. Okay, so this is the basic setting. And then we have identified 3 building blocks that we then assemble our analysis from. The first building block is, first of all, we need to track which places can I actually legally jump to. Then I also need to track the contents of these variables that have this type jump buff t. And then once I have these 2 together, I can use these to propagate the values from the places where long jump happens to the places where the corresponding set jump is. And this then basically means that I account for these flows, and then I become sound in the presence of usages of set jump, long jump. What is the domain that we use to track the contents of these jump buffers and also track the set of currently legal jump targets? This is actually a very simple domain here. We have a set, and this members of the set are tuples from barred nodes. So these are the special nodes that we introduced earlier, and context, and we have simply ordered this by subset inclusion. So, did you still see that one, or? Okay, yeah. Good. Okay, yes, so as I said, we want to track the set of legal jump targets, and we do this context and path sensitively here, and the value of variables that have this type jump buff t in the local state. And then what I do when I do a set jump, 0 in this case, so if I set the jump buffer at some node u in some context alpha, is when I say, okay, for the code that follows now, u bar in alpha is a valid thing that I could jump back to. And I also abstract the value for this argument, update the abstract value for this argument buff to basically this thing that I've just set it to. And then what I do, this set of legal jump targets, I pass it to the callee, because the callee could jump back to any of the set jumps that I have installed as the caller. However, after the return, I restore the set of the caller, because any of these jump targets that have been installed by the callee, the corresponding function has now returned, so they can no longer be validly jumped to. Let's take a look at an example here. So here we are annotating this with L, this is the set of the legal jump targets, and the second component here is the abstract value that we have for this variable error handler here. And first of all, we start out with no legal jump targets, then we go into bar, stays the same. At this point, we actually do the set jump, so we add this element u bar and beta to L. And also the value of this error handler is now this element J1. So this continues the same like here. And then we go into foo. And what happens here, also nothing changes. And then here at this long jump, I basically look up what are the values that I have for this error handler, and all of the values that are possible for this error handler in the set of legal jump targets. And this is the case here. And so at this place I can say, okay, there is no illegal jump here. However, if we continue, so as I said here in foo, nothing changes. If we modify the program again to include our erroneous bit here, then we see that upon the return from bar, we have kept the set of legal jump targets of main. So this is the empty set here. And then later, when I actually do this long jump here, I will see that I'm trying to jump to this J1, which actually is not a legal thing to jump to anymore. So I can report undefined behavior here. So basically what we have now is we have an abstraction of the values of these variables of type jump buff t, and we have managed to basically flag all errors where you're jumping to illegal places. Now the thing that's still missing is I basically need to propagate the values from the call to long jump back to the place where the set jump was called. And if we're given a call to a long jump in some node v in the context beta, and a set j prime of legal jump targets that need to be considered, basically what I do is I do the following. First of all, I check if the jump target is actually in the current function, in the current context. So if alpha is beta and u bar and v are in the same function, then the jump is local, and I can simply propagate the local state to this unknown for u bar and alpha by a side effect. Otherwise, what do I do if it's not local? And then it might be tempting to just do the same and say, well, I can just propagate to this unknown nevertheless, which is actually also what C does. So C doesn't do any sort of stack unwinding here. However, this is problematic. In the abstract, we cannot do this here because we would miss modifications to variables that happen via pointers. Because in our abstract state, at this program point where we call the long jump, we only have abstractions of all of these values that are somehow reachable. So we do not have abstractions of values, for example, of locals, of other functions that are further up the call stack. However, they might have been modified between setjmp and longjmp, which means we basically, in the abstract, need to do the stack unwinding that we actually don't do in C. So what does this look like? So basically what I do is, instead of just doing the side effect immediately, I propagate this value out to the caller. And I do this by making a side effect to a dedicated unknown for jumping out of this function by long jump. And by convention, we always usually call these things red f, if it is the return value for function f. And then we introduce another one that we call red prime f here. We basically store the abstract state that corresponds to leaving f via a long jump. And at this unknowns, we store a map from jump targets to abstract states to be propagated. And then the last thing we do in the long jump is we can also mark the successor as dead, because the control flow is transferred to the set jump, so the successor is definitely dead. Okay, now what happens if I have a call to a function? Now, of course, I need to account for the possibility that this function is sort of left via long jump. And the idea there is that I consult the special unknown that I have introduced. And for each u bar alpha and abstract state s that I find in there, I basically do the check that I did before. I check, oh, is this a jump that is now local to this function? And if it is, I combine the caller state with the value that I have stored at this long jump return and propagate it to this corresponding unknown via side effect. And what this combining does is exactly the thing that I've said before. It adds locals to the abstract state and accounts for these modifications via pointers and so on. Otherwise, what I do is I basically also combine it with the local state to account for the modifications that I have, but then I propagate it out to the caller. Because I say, okay, I long jumped out of this function that I called, but the jump target is not in this function, so it must be one of my callers. Let's maybe take a look at a small example here. This is once again our program. And now we can assume that here at this long jump, we have the long jump target u bar beta. And the first thing I check here is, important to say, so we assume here that foo is analyzed in context beta, bar in, foo is analyzed in context gamma, bar in context beta, and main in context alpha. So here, as I said, I have this target u bar beta. And then I first check, is it inside of the current function, and does the context match? It doesn't, because beta is not gamma. So what I do is I propagate this value here to the special unknown that I have for returning out of foo via long jump. And the new value looks like this. And then when the call to foo happens over here, it will consult this unknown, because it needs to account for the fact that this foo that I just called is not left by a return statement, but by a long jump. And then here I basically do the same comparison, and I look, well, u bar and beta, is this now in this function bar, in this context beta that I have? And yes, here it is. So then as a last step, what I do is I propagate the value that I have here from the foo to this location where the setjmp is called. Now the mechanism looks maybe a bit complicated, but actually very little dedicated mechanism is needed. And the right-hand sides that we use for this analysis are more or less assembled from blocks. No worries. Are more or less assembled from blocks the context-sensitive analysis that uses this partial tabulation approach already needs anyway. So for example, this here would be the right-hand side for a function call edge that we sort of already have anyway. And then the things that we need to add to account for setjmp, longjmp are these additional things here. This looks like a lot, however, notice that this combine abstract transfer function here is also a reuse building block. So the only thing that's happening here is a little bit of shuffling of abstract states, and the rest is basically lifting other analyses. We have also actually implemented these analyses within the static analyzer of multi-threaded programs that's called Goblin. And there, as I've said, we have lifted all the existing analysis in the framework. So we have relational and non-relational value analysis. We have analyses for concurrency bugs. We can detect dead code. We support path and context sensitivity. And by lifting these to support setjmp, longjmp, now all of these analyses soundly account for setjmp, longjmp. We have done some preliminary experiments here. First of all, we have crafted a suite of publicly available litmus tests that we hope further future analyzers who also support this feature might take up. And I'm currently in the progress of also contributing these to this svcomp benchmark set, such that one can also see how other tools do on that. And then we have also looked at libpng, which is actually a widely spread library for the modification of images. And they have shipped this PNG test application with it. And in this PNG test application, we ran our analysis. We basically produced 6 warnings. 2 of them were warnings about accessing a local variable that has been modified between the setjmp and the longjmp. And it turns out that these 2 warnings seem to be actual bugs in the implementation there. There is undefined behavior. For some complicated reason, the compilers do not manifest it, so one cannot actually observe it. But technically, we basically identified 2 real bugs in this libpng program. And very similar usage patterns have in the past already led to a memory leak in ImageMagick. So it's very plausible that these are real issues. Yes, so to sum it up, what we have given is a technique to lift existing analysis to support setjmp, longjmp, and we have made use of side effects to do this in a convenient way. We track the control flow for correct usages, so we are sound if people are using it correctly. We also flag issues if people are using it incorrectly. And we have implemented all of this in the Goblin framework, done some preliminary experiments, and have also provided a set of litmus tests for future analyzers. And with that, I'd like to thank you and look forward to your questions.
Thank you. Any question?
I think it's very interesting because, as you said, many analyzers just ignore the jump functions. From your experience, like how many of the current C and C++ programs are still using those?
So I do not have precise empirical data. We looked a little bit. So it seems to be very specialized places where people are using it, and then they're using it a lot. So for example, if you want to use this libpng library in your program, then you have to use them. But it's not like every C program that you will find out there will make use of it.
Okay, we have a question from Discord from Niazza Fanella. How often are, yeah, I think it's the same question. And actually it was also my question. Yeah, often set jump, long jump used in industrial C code. If I remember correctly, their use is deprecated or forbidden by most coding standard, for example, Misra C.
That is very true, yes. So Misra C, for example, it does explicitly forbid it, yes. And I mean, if one looks at the list of issues that there are with it, I think it's also a good thing that one should probably not use it.
Thank you. Other question? Let me check here. Enia is replying. Yes, same question. Let's see. Okay. Okay, so another question. So thanks again.
Thanks.
Thank you. And, oh, sorry.